Just to give you guys a quick introduction, my name is Cheng. I did start Flex Logix. I think over the past few years, I have spoken with you guys about the architectures that we have been developing, mostly for accelerating AI inference. And therefore, we came up with this NMAX architecture. But actually, from talking to customers, today I would like to talk to you about one of the other applications that the customer have asked about and turned out to actually have worked out quite well for us, and that is to accelerate DSP, starting with filters, using the NMAX architecture. So let me try to scroll the slide here. So not going to bog down in any of the introduction stuff. Basically, we are an IP company when it comes to the NMAX core, right? It is a silicon IP that was with its full software stack for front-end compiler that basically does a high-level synthesis down to control circuitry, which is at a Verilog at a gate level. And then there is the back-end, which is the compiler, which does place and route. The full stack of software is developed with the hardware to provide primarily acceleration to AI inferencing. But over the past year, some of the customers have gotten excited about our capabilities when it comes to computation, and asked us, "Hey, can you guys use these for DSP purposes? You have a lot of Macs, you have a lot of memory. Can those things be used for DSP?" And since you have a reconfigurable hardware structure, a lot of our customers are coming from FPGAs right now. So they go, you look like you have FPGAs like circuitry. You have way more Macs at way more frequencies than what FPGAs are generally capable of. Can you use this to build me my filter, build me my FFT and things like that? And this was a hindsight for us. We didn't design NMAX topology for that purpose. But after doing some research into our existing architecture, we realized it's actually extremely good at filters, much faster than what traditional FPGAs can do at a much lower power performance area cost to the customer. So we have customers now planning to use this for DSP right now. And as you will see, it's actually not as good as it could be. We can easily get to a factor of 2 from some improvements in the topology, which you will see later. And then, of course, it can be further extended into other applications for signal processing, namely, FFTs and things like that. But a quick overview of what's in the core, right? Each one of the tile is 1,000 multiply accumulator operators. So that's why it's called NMAX 1K tile. There is 16 of these instances of computational clusters. Each one of those clusters has 64 Macs inside, and it is basically at 8x8 integers, unsigned, or signed will be 9x9, or 16x8, or the weight, or in the filter case, the coefficients will be a signed 9-bit number or unsigned 8-bit number. The signed 9-bit cannot be the full range, but it's basically a signed 9-bit where there's 8-bit of dynamic range, but a 0 could be anywhere. So it's very much like in the AI case where it's an 8-bit of dynamic range, but the bias for the 8-bit can be anywhere in that signed 9-bit range. So for natural signal processing, it actually turns out to be pretty useful. And of course, that's at full throughput, and at half throughput, we could do full signed 16x16 or unsigned 16x16 integers, as well as BFlow 16x16, which is just FP32 with fewer bits of mantissa. And when it comes to processing of those natural signals, especially whether it's image or sound, you will see that this dynamic range is much more important than the extra bits of mantissa. So, for FP32 signal processing, BFlow 16 comes very close. And I think, the advancement in AI has contributed greatly here to filtering as well, because nobody was doing BFlow in the filter back in the days until these AI guys came along and recommended them. And another thing that you may or may not know about is Winograd acceleration was originally designed 30-40 years ago to accelerate FIR filters, or just filters in general. So people have adapted them to accelerate AI signal processing or AI CNN convolutions, but basically, naturally, Winograd will accelerate filtering. Of course, we only built Winograd at that time to accelerate them in the 8-bit coefficient mode, not the 16-bit, and that's something we have to live with for now. So the customers that needs the full 16-bit of coefficient precision will not be able to use Winograd, and you will see that all the later slides that we have do not assume this acceleration. Now, in the cases where they could be accelerated, the compiler automatically does it for you, so you wouldn't actually have to do anything other than just loading the same high-level model and then program it through. In the AI space, we program them through the TensorFlow or the Onyx framework, but in the case of DSP acceleration, we actually have to come up with another flow to read the customer's, spec for the filter. The filter spec is not very hard to read, but would like to integrate it to something more high level, like something from a MATLAB, whether it's a Simulink output or some kind of a MATLAB code that is easily parsable. That will be something of interest to us. And of course, the tiles can tile together to the array to give you more capacity in terms of compute, more capacity in memory, more capacity in pins. That's the same as what we've had before. It's a very scalable architecture. Both the hardware and the software that supports it can scale seamlessly, meaning if you have a bigger array, the front end of the compiler can automatically infer more parallelism, more layer fusion, and then the back end of the compiler automatically times, places, and routes across all of these tiles as if it's a seamless fabric. And of course, when you grow the tile, you get more L2 memory attached to it as well. The L1s and the L0s are inside the tile. The L3s is what we call, on chip, not necessarily on the array anymore. It's treated the same at that point as off chips such as DDR or PCIe access. Basically, you have to go through DMAs to get them. But L2s are physically attached to the array, so they can be accessed on a 1 cycle latency as opposed to a DMA fetch and request and act kind of thing. So as you know, at this point, this chip was taped out. It actually ran at 933 instead of 1066 because the LPDDR that we're working with and the package and the substrate turn out to only be able to operate at LPDDR 3733, which is probably the most common high-speed LPDDR. There's very few working 4266, and we also had trouble with our vendor in achieving that. So in full honesty, it's still very close to 1 gigahertz, but right now it's rated for 933 at the chip level, even though the core itself could go a little bit faster than that. And this is available as the chip as well as the PCIe card, and we'll have samples available for you by Q3. So we're very excited about sharing you real silicon numbers by then in your fall conference. And in the meanwhile, Thursday morning we have our Vinay, our technical marketing manager for AI, to share more of these real world applications with you. Real customers working with us on real models, and we want to show you how we stand against real customers, the big guys of today. But for this talk, we're actually, on this nice little tangent when we're talking about filtering. So many customers, as you know, are now using expensive and have been using for decades expensive high-end FPGAs for DSP, and not just testers, but primarily in 5Gs and base stations, radar imaging. Those are high sample rate, large number of taps, and for those of you that are signal processing experts, even if you have a 4 giga samples per second filter, for example, you don't need a 4 gigahertz FPGA. You can do an 8-phase polyphase filter and run everything at 500 megahertz. And that will work for you still. You just need them to spread them across 8 parallel paths, and that's what polyphase filters does for you. So there's a lot of that kind of implementation that allow you to not have to run as fast as the speed of your incoming signal and still be able to get the signal processing that you're looking for. But still, more frequency always give you more throughput. People are simply dividing it down because they have to, not because they want to. And these large, expensive FPGAs or high-end DSPs, hundreds of dollars, is generally what people are buying today. And we have one customer say they buy these high-end FPGAs, where about a third of them are DSPs, And that's all they use. They don't really use anything else, but they have to buy the high-end FPGAs just to get the most amount of DSPs they can get in a single piece of silicon. So, you know, our customers are asking if we can do signal processing based on what we have today. So we'll dive into our filtering architecture really quick. And I hate showing people FIR filters because I feel like all of you guys here have seen this so many times. But just to give you a quick example, you know, this is a filter that has been delayed, where the input data is delayed every cycle. And then every delayed version of this input data is multiplied by a unique set of weights, which is coefficients, and then accumulated in the end of the day to form the output of the FIR filter. So you see X is the incoming data, K is the coefficients, and Y is the accumulated output. So generally, the incoming data is running at some high number, you know, of megasamples or gigasamples per second. And then if it's too high, you will have to switch to a different architecture, such as polyphase, where you are round robining between different parallel paths of incoming filters. Those of you who know polyphase filter knows that very well. So, you know, there's tricks that you can do. And actually, it turns out this maps to our architecture rather beautifully. So we already have this, you know, native structure where the data can come in and flow through the taps and flow out, and the accumulated data as well as the incoming data can both flow out of the MX array and or the MX cluster, and that's important because the input data has been delayed in this case by 32 cycles, which can then feed into the next guy. Now, for you that have a photographic memory may be asking us, why is this not 64 taps? Right? That is because we didn't design this for FIR filters, so we actually have to take a loss in MAC utilization just to be able to map these coefficients as weights in a special way so they can accumulate as if it is a FIR filter. So that's this version of the hardware, because of course we didn't design it for FIR filters, but then the next version of the hardware, there's simple changes that we can make that will gain us back that factor of 2. But basically the concept is the same. Input data go in, gets delayed in this chain and flows out and can flow out to the next chain to be further computed, and the MAC accumulated value can also go out to the next cluster to be delayed and computed even further. And the L0 SRAM, which normally holds the weights for the matrix multiply, is now placed with filter coefficients in an intelligent way so that the output of this a MAC cluster produces the output of the FIR filter. Excuse me. And just to give you an idea of what's happening here, the L0 SRAM in each stage is holding the coefficient value of the SRAM, and the incoming data has been delayed every cycle so that each tap sees a 1 cycle delayed version of the data, and then the accumulated output is what is sent out in the end of the day. Now this is actually for a 16 by 10 bit integer. You may ask, why is it not 16 by 8? It's because due to a lot of reasons, the internal precision of our multiply accumulation is actually 16-bit signed by 10-bit signed, which you will actually find to be sufficient for most signal processing applications. But out of the interest of fairness as well as compatibility, we are aware that a lot of the common benchmark and data for filtering is published on 16-bit by 16-bit filters, where the coefficient of the filter is also a 16-bit value instead of a 10-bit value. So you will see that for the rest of the slide, all of the benchmarks that we use, we only use the higher precision and not the lower precision. So that's just out of the interest of fairness. And of course, we can support bflow 16 as well as integer 16. In the case of bflow 16, it will be an FP24 multiply accumulate output, which is, you know, in terms of dynamic range the same as BF16 and also the same as FP32, but just with more mantissa or fewer mantissa of fractional precision. As you can expect, as I've touched on, the clusters can be daisy chained to form longer and longer FIR filters. The minimum filter size is 1 cluster. Even if you don't need all the taps in 1 cluster, you cannot fit multiple filters inside one, just because of the way this is architected. But you could, in a maximum case, cluster all the taps of all the clusters and basically form an extremely large filter if that's what your requirement is. And just like MX, this can be reconfigured on the order of microseconds. Now, you may not need to reconfigure your filters this quickly, but you can. There are cases where the filters are, adaptive. There is a lot of adaptive filtering in the recent decades. So there is definitely benefits to reconfiguring these coefficients. And just like the weights of the AI model, it can be the weights, the coefficients of the filters can be updated in the background and then simply move to the foreground when all the weights have been updated. So there's not a lot of downtime when the filter coefficients have to be updated. Now, if the filter architecture has to be updated, that will require a reconfiguration of the MX array, just like when you switch from one layer of the neural model to another layer of the neural model. Okay, and just to show some simple math here, if you run at 1 gigahertz and you have a 1 gigasample per second input signal, each cluster can give you 16 taps of 16 by 16 integer or bfloat by 16, or bfloat 16 floating point signal processing. So one tile can give you 256, and of course a 2 by 2 array in our case can give you 1,000 taps. If your sample rate is only half of that, we can actually take advantage of that and give you double the number of taps. So you could have a trade-off there between your throughput requirement and the number of taps that the computational clusters can give you. Now, we even support complex signal processing. A lot of communication signal processing requires that. That will run at just one half of the sample rate at 1/4 the number of taps, because complex filters is actually 4x of what it is in terms of the number of Mach units that are required. So just to, again, keep in mind, if you need integer 10 by int16, you get 2x the throughput of what you've shown here. And that's based on our current hardware. By making a simple change to our hardware, we get 2x of even that. But everything that we're showing here is based on what we can do today, based on our current hardware. Okay, so we compare that to an FPGA. There's virtually no comparison. Even if you take the fastest Vertex Ultra scales out there, you may be able to hit 800 megahertz if you really push the DSP, and that's only if you have up to 21 taps. So like any FPGAs out there, the DSPs comes in columns, and the columns are only so tall. Once you go outside of one column, you have to go through interconnect fabric and lookup tables, and then your performance goes way down. So if you need more than 21 taps, your performance is much, much lower. The estimations that we get out of Vivado is around a factor of half. You lose about half the performance when you have to use more than 21 taps in a chain. And we don't have that problem, obviously, but that's what they have.
Cheng, if you could try and wrap up, we have to go to the Q&A.
Of course, yeah. And an FPGA with 2,000 max and 2,000 taps, that's hundreds of millimeters and hundreds of dollars. And just to match their performance and match their computational density of 1,000 taps, we need just 26 millimeters of an MX array. So to do some quick comparison against what's out there, even if you take the highest end DSPs, it's still more than $100 if you buy them in volume. We're still more than a factor of 2 better than they are, being able to run more filters in parallel, and is more scalable. if we compare to the CVAs out there, the newest, greatest DSP in 7 nanometer, we're still slightly faster in a much lower frequency, in a much older process. And again, all these things are using integer 16 by 16. So we're not accounting for our quantization performance improvements, as well as our future performance improvements that can easily be done and get us another factor of 2 in the kind of filter signal processing.
Okay,
So,
we should go to the Q&A now, Cheng.
Sure. I think that's pretty much my last slide anyways. So go ahead and let me know if you have any questions.
So had a question coming in about the memory hierarchy. I had some questions myself. You've described this before in the context of using NMAX for AI acceleration. Question was about the L2 cache. Does it have 1 cycle latency, and what about the L1 cache? Maybe you could answer that in the context of, now you've got this memory hierarchy. How does that get used for a DSP application?
Yeah, so basically the L2 cache does have just 1 cycle latency, but based on how far your tile is, you know, the interconnect signals may be pipelined as it gets there. So, you know, it may not be a 1 cycle latency, but it wouldn't be hundreds of cycles either, right? You know, even if you have to go from one end of the 2x2 array to access an L2 SRAM block that is diagonally on the other side, you flop by no more than 4 or 5 times. So that's 4 or 5 times for the control to get there, 1 cycle for the data to come out, 4 or 5 times for the data to come back to you. You're looking at 11 clock cycles, you know, from 2 ends of the silicon. Now, you know, what I mean by this 1 cycle latency is this is different from our L3, which is at the SRC level, or DDR or PCIe, because those, you basically will have to make a request, and then the DMA will then ask you when it brings the data back, and that's when the data is stored in a local memory or a local cache, and then you go and read from there. So there is no handshake when it comes to L2 access. It is simply an SRAM access. It will take some number of cycles for the control to get there if you're far away, some number of cycles for data to get back to you in that case. But other than that, there is no latency other than just a natural SRAM read.
And then along with that question was whether the L2 can be shared between tiles.
Of course, I think I answered that question already. The L2 can be shared between tiles. So basically, you know, if you have a number of compute units that have to be multiplexed onto a single piece of SRAM, there will be a MUX that's implemented in the soft logic, which is the FPGA fabric. All the signals come in, the soft logic will have to control the memory access in the scope of who gets the data when. But yes, you know, it's basically an FPGA fabric. The block RAM can all be shared if your RTL is programmed that way.
Okay, this is a very specific question about a 32-tap FIR filter. Mm-hmm. Is the output clock rate limited by the multiplier or by the summation of the various taps?
Well, depend on which mode you're in. Again, this is the hardware that we have previously built for AI. In the integer mode, it's definitely the multiplication because the integer adder is relatively trivial. But in the floating point mode, it is the floating point MAC that is the bottleneck for the accumulation. So based on which you're talking about, in the integer, it's the MAC, it's the multiplier. In the floating point, it is the adder. I'm asked to rate my own presentation.
Yeah, sorry.
I will skip that.
The audience, please go ahead.
Contaminate your data.
Yeah. And we get a frequent question. I'll just take the opportunity to answer. People asking about the recordings. Those will be available a few days after the conference ends. All the sessions are being recorded.
Mm-hmm.
A question just to clarify, since you have both NMAX IP and then as a chip, mm-hmm. In the positioning, you talk about, say, you know, against like something like CEVA's DSP, but that DSP is designed to do 5G basebands. So if you're just comparing IP to IP, mm-hmm. Would people choose, say a smaller DSP that just does filtering versus all the other functions you get in an XC16? Why would they choose an FPGA implementation versus a dedicated DSP block?
Yeah, I frankly think in the end of the day, it comes to the how much acceleration do you get, right? This is an IP, but as you can see, we have been putting them into SoCs based on demands. You know, I'm not going to comment whether we intend to do the same, but you can probably guess those who are integrating IPs is going to evaluate this from an IP perspective only. For those who buy FPGAs, it's going to evaluate this more from a chip perspective, which means what is the power of my silicon, what is the cost of my silicon, and how much can this piece of silicon do for my filtering applications, right? So those who are buying FPGA chips today, they likely is going to want a chip version of whatever I just talked about.
Okay. So I imagine that one of the nice applications would be you could have multiple tiles on a chip, and one would be running DSP, another could be running AI.
You can, but right now the compiler is set up. So sure, if you have multiple arrays, not a problem. But right now the compiler doesn't support co-execution of DSP and AI at the same time. Now, I don't think we need to, because I feel like it's much better for the model to finish running and then reconfigure it, because this thing is reconfigured all the time anyways, and then reconfigure it for a DSP application. And then of course you can keep on loading the configuration file for a DSP purpose versus an AI purpose.
Sure. Okay. What is your plan for the software support? You mentioned something about MATLAB.
Exactly. So, you know, unlike AI hardware, the software for filtering is much, much simpler. A lot of our customers are designing filters in MATLAB, which of course you can export a filter file at the output of that, which defines how many tabs you have and the value of that tab. It is a very simple parser that then just maps to our soft logic. Compared to parsing AI models, this is night and day. This is much, much simpler. Yeah.
Okay, and so when is this going to be available?
Well, you know, so the customers that we have right now, they are engaging. We are actually in the middle of doing another port for them. So, you know, that's the part that is coming. So it will definitely be released to them sometime next year.
Okay.
But of course, if the customer just want to evaluate it on our current silicon, they can do that once the silicon returns in Q3.
Okay, great. Maybe we can just fit in this one more question before the break. In your FIR filter example, you gave delay. Does the design compensate for the registered data path?
Yeah, so basically in the FIR filter, the input is delayed and the output has to be accumulated, where each tab has a delayed version multiplied with its own coefficients. And then the output simply has to be correct, right? There will be a latency with any FIR filter, whether you use a DSP processor or a Cheng structure as you see in the FPGAs. The output has to be correct. So, you know, does the design compensate for the registers in any logical way? Well, it compensates them in a way where it has to be logically correct. So you know, the weights has to be kind of intelligently placed. Otherwise, in the end of the day, your filter don't accumulate to the correct value.
Thanks, Cheng. That takes us to the bottom of the hour. So it's a 10-minute break. We'll resume with our next presentation at 20 minutes before the hour. See you then.